So let us proceed and let's talk about the energy in SHM. Okay, so let us discuss energy in simple harmonic motion. So first of all, let's talk about potential energy. Okay, so now in SHM, we know there is a force. Okay, force is given by what? It is given by Hooke's law. Okay, so the restoring force is given by Hooke's law. It's equal to restoring force is given by what? Minus of k multiplied by x, the Hooke's law. Okay, so for small displacement dx, how much would be the work done? Work done against this restoring force would be equal to dw, that is kx dx, right? We want work done against this force. Okay, so the total work done in displacing it from some x1 to x2 is suppose w. Okay, this is work done for displacement from, let's say, 0 to x. Okay, let's suppose x1 is 0 and x2 is just equal to x. So what do we get? So this work done is equal to what? It is integral of kx dx from 0 to x, and this is equal to, we can take k outside, so it is just integral of x dx, so it is x square upon 2. Okay, so it is half of k multiplied by x square. This is the work done, and this is also the potential energy stored in the spring block system. Okay, or a system which is performing SHM, right? So we get formula for potential energy. So potential energy in SHM, U is equal to what? It is half of k multiplied by x square. Okay, so this is simple. Okay, this is formula for potential energy. Similarly, we can find out kinetic energy. So kinetic energy is given by half of m into v square. And what is v? So v is omega multiplied by square root of a square minus x square. Okay, so it is half of m multiplied by omega multiplied by square root of a square minus x square. This is the formula for speed. Okay, we want square of that, so it is half of m omega square multiplied by square root of a square minus square root of a square minus x square square. Okay, so that is just a square minus x square, and then we can use the formula for the k. Okay, spring constant. So we know omega equals to square root of k by m, or omega square is k upon m. That means k is equal to m omega square. Okay, so we can use that here, and we can write potential energy is half of m omega square multiplied by x square. Right, this is another formula for potential energy. And similarly, we can write down for kinetic energy. Okay, m omega square is equal to k, so we get this is equal to half of k multiplied by a square minus x square. Okay, so we get another formula for kinetic energy also. So this is simple. This is potential energy and this is kinetic energy. Then we can add these two and we can find out the total energy. So total energy is given by T equals to U plus K. T equals to U plus K. Okay. So what is U? U is let's use this formula, half of k into x square, and this formula for kinetic energy. So we get half of k multiplied by x square plus half of k multiplied by a square minus x square. So if we just multiply this half k with these terms in bracket, we'll get half of k into a square minus half of k multiplied by x square. So that minus half k x square and this plus half k x square, it will get cancelled out, and we will get half of k multiplied by a square. This is the total energy. Okay, or in place of T, I will just write TE, total energy. It's given by half of k multiplied by a square. Okay, then we can substitute k equals to m omega square. So we get half of m omega square a square. This is total energy. Okay, this is formula for total energy. After that, we can plot these. Okay, we can plot this. So actually same thing we had done in work energy and power also. Okay, these are same formulae, right? So if we plot potential energy, we'll get this kind of curve. Okay, for kinetic energy, so this is the mean position, x equal to 0. On this axis, on this vertical axis, we are plotting all the energies. Okay, and this is total energy, this is kinetic energy, and this is potential energy. So at x equal to plus or minus a, kinetic energy is minimum, that is velocity is equal to 0. Its maximum here at x equal to 0. Okay, because speed is maximum at x equal to 0, that is the mean position, and potential energy is minimum at x equal to 0. So potential energy is 0 at x equal to 0, and its maximum at x equal to plus or minus a. Then let us plot energy versus time. Okay, potential energy and kinetic energy versus time. Let's plot. All right. So now let's suppose a particle is starting from some position. What? Let's suppose it starts from the mean position. Okay. So suppose particle starts from mean position. So if we draw a graph of x versus t. So suppose particle starts from mean position. So if we draw a graph of x, that is position versus time, what kind of graph do we get? So at x equal to 0, it will be at 0, that is at mean position. Then at t equals to t by 4, okay, at t equals to 0, it is at x equal to 0. At t equals to t by 4, it will go to positive extreme position, right? It goes here at plus a, then again it goes to 0, again it comes back, right? Then it goes to negative extreme position, that is at minus a, again it comes back. Okay, again it goes to positive extreme position. So the graph will look like this. Okay, the graph will look like this. So this is x equal to a sine omega t. Okay, so this is t by 4, this is t by 2, this is 3t by 4, this is t, okay, this is 5t by 4, so on and so forth, right? Then next I want to plot the graph of potential energy. Okay, next I want to plot potential energy U. So see, potential energy is given by what? It is half of k multiplied by x square, right? Potential energy is given by half of k multiplied by x square. Okay, so here you have x like this, you will take square of that. Okay, so you will get some positive values. So x square is something like this. Okay, but when x is negative, its square will also be like this only, right? Okay, so this graph will look like this. Okay, the graph of potential energy versus time. I'm sorry. Now you need very delicate hands to draw this. It will look like this. You can imagine this, right? Okay, so is it clear? Is this graph clear? Okay, so this is graph of potential energy. It's always positive, and its maximum value is this thing, which is half of k a square. Okay, and formula for potential energy is half of k into x square. So see, when does it become maximum? It becomes maximum at t equals to t by 4. Okay, when particle starts from the mean position, it goes to the extreme at t equals to t by 4. Okay, then because it goes to extreme, the potential energy becomes maximum. Okay, and what about kinetic energy? So the graph of kinetic energy will be, it will be like this. Let me use different color. Peak values for both of these will be same, half of k into a square only. So this will be the graph of kinetic energy k versus t. Are the two graphs clear? So now let us try to solve some problems based upon this. Okay, so just wait for 1 minute. Let us try to solve some problems. So see this problem. Which one of the following equations of motion represents simple harmonic motion? I'm sorry. Okay, tell me, acceleration equals to minus k x plus a, acceleration equals to k x plus a, acceleration equals to kx, and acceleration equals to minus k naught x plus k1 into x square. Which one of these represents simple harmonic motion? So option A, right? Okay, because you want a force which is always directed towards the mean position. So here, let's suppose mass is equal to 1. So force is minus k times x plus a. Okay, that is minus ka minus kx. Okay, or here you can say the mean position is a, x equal to a, right? Okay, the mean position itself is x equal to a, and this force is directed towards that position. Okay, so option A is the answer. This is simple. Now the questions that we are going to discuss are all simple. See, this one, a particle executes SHM along x-axis. The force acting on it is given by. Tell me, it's option D. See, in option C, what is the problem? Here, force goes on increasing. The restoring force goes on increasing as x increases. That means there will not be uh, any restoring. Okay. On the contrary, it pushes that object. Okay, it pushes that object away from the center. Okay, so C cannot be an answer. Only option D. Particle of mass m is released from rays and follows a parabolic path as shown. Assuming that the displacement of mass from the origin is small, which graph correctly depicts the position of particle as a function of time? So see, particle is released from here. Okay, that is from this position. So which is the answer? Then because potential energy function is like this, it will perform simple harmonic motion. Okay, so which one is answer? Option A is position versus time graph of simple harmonic motion. Option D is position versus time graph for simple harmonic motion. Which one is correct? Simple, has to be option A, right? It is option A because particle is starting from here. It's starting from extreme position, not from mean position. Okay, so it's option A. The particle executing simple harmonic motion has a kinetic energy k naught cos square omega t. The maximum values of the potential energy and total energy are respectively: A is k naught upon 2 and k naught, B is k naught and 2 k naught, C is k naught and k naught, and D is 0 and 2 k naught. Tell me the maximum values of potential energy and total energy. Let's do one thing. This is kinetic energy is given by k naught cos square omega t. It's option C, right? It's option C. Okay. So why so? Why so? So kinetic energy is given by this formula k naught cos square omega t. So now you can compare this with some x, which is, if x is a sine omega t, okay, then v will be a omega cos of omega t, and then if you square this, okay, then v square will be square of this a square omega square cos square omega t, right? And the formula of kinetic energy will have cos square omega t term. Okay, so then you can, I'm sorry, you can compare this. Okay, so let's do this. So it is half of, let's take half of mv square. It will be equal to half of m multiplied by a square omega square cos square omega t, right? So this half of m omega square a square, this is the total energy. So k naught is equal to this thing. Okay, so k naught is equal to half of m a square omega square, and this is equal to total energy, right? And the maximum value of potential energy just equal to total energy. So total energy is also k naught, and maximum value of potential energy is also k naught. Okay, that's why it is option C. See, the potential energy is given by this thing half of m omega square x square, right? What is the maximum value of potential energy when x is equal to a? Okay, it is half of m omega square a square. And what is maximum value of kinetic energy? It is also same. Okay, when x is 0, kinetic energy will be maximum. It is half of m omega square a square. Okay, and total energy is also that much, half of m omega square a square, right? So now in our problem, what is the maximum value of kinetic energy? This is the problem. Huh. What is the maximum value of kinetic energy? It's k naught, right? So maximum value of kinetic, because maximum value of cos square omega t, okay, it's 1. Therefore, the maximum value of kinetic energy is k naught. It must be equal to total energy. Okay, so total energy is equal to k naught, and the potential energy is also equal to maximum value of potential energy is also equal to k naught. The potential energy of a simple harmonic oscillator when the particle is halfway to its end point is, now E is supposed to be total energy. Okay, so in comparison with that, what is potential energy when particle is halfway to its end point? So we know that potential energy is half of k into x square. Total energy E is half of k into a square. So when x is equal to a by 2, how much would be potential energy? Half of k into a by 2 square. Okay, that is a square by 4. Okay, so that 1 by 4 I can take here. So it's 1 by 4 multiplied by half of k into a square. And what is this? This is equal to E. Okay, so it's 1/4. It is 1/4 of E, right? So option C is the answer. Let us see this question. This is from 2003. A particle of mass m oscillates with simple harmonic motion between 2 points x1 and x2. The equilibrium position being 0, its potential energy is plotted. It will be as shown below in the graph. This is very simple, straightforward. So option A. Okay. Next one, the displacement between maximum potential energy position and maximum kinetic energy position for a particle executing simple harmonic motion is. So yes, tell me, is it plus minus a by 2, plus a, or plus minus a, or minus 1? Option C, right, it's option C. See, because okay, displacement between, or you can say difference between maximum potential energy position and maximum kinetic energy position for a particle executing simple harmonic motion is. Okay, so see, we consider a particle which is oscillating like this, performing simple harmonic motion. This is plus a. Okay, let's use small a. This is minus a, and this is 0. Okay, so now if you take maximum potential energy, so it is at this position and it is at this position. So if you subtract uh, okay, x equal to minus a, sorry, if you subtract 0, okay, at 0 kinetic energy is maximum, ke is maximum, right? So you subtract this position from minus a, what do you get? Minus a minus 0 is minus a. Okay, and if you subtract it from plus a, then you will get plus a. Okay. So these are the two positions where potential energy is maximum. Okay, so that's why it is plus minus a, right? Next question, the total energy of particle performing simple harmonic motion depends on, so KAM, KA, KAX, KX. Total energy can be written as half of m omega square a square. Okay, so in this case, you can say it depends on m, omega, and a, right? So it depends on m. Okay, and it can be also written as half of k into a square. So if k and a is given, there is no need of m. But if k is not given, then you need m, omega, and a. Okay, right? But if k is given, we don't need m. So k is answer. Okay, option B is the answer. A linear harmonic oscillator of force constant 2 multiplied by 10 raised to 6 newtons per meter and displacement 0.01 meter has a total mechanical energy of 160 joules. Its potential energy, okay, we have to calculate potential energy, and it is simple, right? So force constant is given, displacement is given, potential energy is equal to half of k times x square. This is just plug and play kind of problem. Half of k, 2 multiplied by 10 raised to 6 multiplied by displacement is 0.01. Okay, I can write that as 10 raised to minus 2 and we have square of that. Okay, so this 2 and this half gets cancelled. Okay, so we have 10 raised to 6 multiplied by 10 raised to minus 4, that's 10 raised to 2. Okay, 10 raised to 2, 100. So 100 joules is answer, option C. So in simple harmonic motion, when the displacement is one half the amplitude, what fraction of total energy is kinetic? So we have just found that when displacement, yes, so in a simple harmonic motion, when the displacement is one half the amplitude, what fraction of total energy is kinetic? So can you tell me the answer directly? It's option B, right? Because potential energy is 1/4, remaining is kinetic energy. Okay, so we just calculated, right? Potential energy given by half of kx square, x is equal to a by 2. Okay, squaring that, we get what? It is 1/4 of half of k into a square, which is E. Okay, so it is E by 4. This is potential energy. We want kinetic energy. So it is total energy E minus potential energy U. Okay, this E minus E by 4. That is 3 E by 4. Okay, so what fraction of total energy is kinetic? It is 3/4. A loaded vertical spring executes simple harmonic motion with a time period of 4 seconds. The difference between the kinetic energy and potential energy of the system varies with a period of 2 seconds, 1 second, 8 seconds or 4 seconds. So see, it is performing simple harmonic motion, right? It is performing simple harmonic motion. And if we talk about the potential energy and kinetic energy in simple harmonic motion, so we have this kind of a curve. Okay, this kind of a curve. Now they are saying if we take difference of this, okay, difference between potential energy and kinetic energy. So what? Sorry, what kind of graph we'll get? Or see, both of these, okay, they are periodic. They are periodic with period of t by 2. Okay, see, potential energy and kinetic energy. So if period of SHM is this much, it's T, then the period of potential energy and kinetic energy is how much? It's T by 2. Okay, so even if you take the difference, because both of these are periodic with period equal to T by 2, the difference is also periodic with period equal to T by 2. Got it? Yes, no? And that's why here time period was 4 seconds. Okay, time period of SHM is 4 seconds. So time period for difference between the potential energy and kinetic energy, or kinetic energy and potential energy, okay, if you take difference of those, so this function k minus u, this is also a periodic function, okay, is periodic with period t by 2, okay, because both of these are separately periodic with period t by 2. So even if you take difference, their period will be same, okay, its period will be same, okay, and that's why the answer is what? T is 4, so it is uh, 4 divided by 2, okay, 2 seconds, option A. Let's see next question. A body executes simple harmonic motion with an amplitude A. At what displacement from the mean position is the potential energy of body is 1/4 of its total energy? So this is repeated. Tell me, the question is, at what displacement from mean position is potential energy 1/4 of total energy? So potential energy U is equal to what? E by 4. Okay, this is given. So half of k into x square is equal to 1/4 of half of k a square. Okay, this is E. Half k a square is E, right? So then, okay, this k and k gets cancelled. Okay, half and half gets cancelled. X square is equal to a square by 4. So x is equal to a by 2, right? The angular velocity and the amplitude of simple pendulum is omega and small a respectively at a displacement x from mean position. If its kinetic energy is T and potential energy is V, then the ratio of T to V is ratio of kinetic energy to potential energy is. So that is simple, right? Kinetic energy is half of, okay, I'm sorry. Yeah. So you see here it's a square minus x square is there, right? So we can use this formula for kinetic energy. It is half of k multiplied by a square minus x square. Let's use small a. Okay, half of k multiplied by a square minus x square. And formula for potential energy is half of k multiplied by x square. So this half k and half k gets cancelled. So what is left? It's option C. Okay, this is equal to a square minus x square divided by x square. Right, it's option C. Next, let us discuss one topic. Okay, let's talk about time period of a simple pendulum. A simple pendulum. Okay, so what is a pendulum? We know what is a pendulum. It's a structure in which you have a thread, or let's suppose a rod, okay, thin rod, and a bob. Some mass is connected at one end of that, okay, rod or string, you can say. So that kind of structure is known as a pendulum. So let's suppose this is a rigid support and we have got one pendulum This is the mean position of that pendulum. Okay, and it is pulled by some angle. It is pulled by this much angle and released. Okay, and released. So what will happen? It will perform oscillations like this, back and forth, back and forth. Okay, so we want to find out the time period of this pendulum. Okay, so let's do that. So let's suppose this angle is theta. So now when it is pulled, okay, when it is at the extreme position, what are the forces acting on it? So one force you can say is the gravitational force, which is acting downwards. Okay, mg. And other force is tension in the string. Other force is tension in the string, right? So now we'll find out the torque acting on this pendulum. Okay, so how much would be the torque? So see, there are these two forces. So let's find out torque about this point. Okay, the point at which the string is fixed to the rigid support. So now if you think about this force, okay, which force? Tension in the string. It is passing through string itself, right? It is passing through string itself. So let's suppose it acts at this point. Okay, so its distance from this point, okay, its distance from O is equal to L, right? But it is passing through the string itself, and therefore torque due to T is equal to 0. Okay, so what will be torque due to T? It is equal to what? T multiplied by L multiplied by sine of the angle between two, and sine of the angle between two is what? Sorry, angle between two is what? 180 degrees. Okay, this is R and this is force. Angle is 180 degrees and sine of 180 is 0. That's why there is no torque due to this force. Okay, then there is other force, the gravitational force. So how much is torque due to that? So torque due to the gravitational force. Okay, so torque due to gravitational force is what? It is the force mg multiplied by this distance, okay, L you can say, multiplied by sine of the angle between two. And how much is angle between two? So see, the position vector of this force, okay, it is this one. Okay, this is the position vector. You can say it's R. Okay, so R is directed like this, mg is directed like this. So this is the angle. Okay, this is the angle between the two, right? So angle is theta. Okay, so it is force multiplied by, so I'm sorry, it is R multiplied by F multiplied by sine of the angle between two. Okay, sine theta, right? So mgl sine theta is the torque. Is it clear? Yes, no? Okay, then we can write torque is equal to I multiplied by alpha. Okay, it is I multiplied by alpha. What is I? It's moment of inertia. So it is I alpha multiplied by mgl sine theta, and I will put a negative sign over here, okay, for the reason that I will explain. Okay, so what is value of I? What is value of I? It is ml square, right? It is ml square, moment of inertia of this mass. It's just mass multiplied by distance square. Okay, so it is ml square multiplied by alpha equals to minus of mgl sine theta. Okay, and let's suppose this angle is very small. The angle is very small. Okay, so for small angles, sine theta is nearly equal to theta itself. Theta measured in radians. Okay, so I'll replace this sine theta by theta itself. Okay, so now see, why is this negative sign there? Because the theta, okay, the angular displacement and the torque, they are in opposite direction. Okay, so if you think about the displacement, angular displacement and the restoring torque, they are in opposite direction, and that's why we have put this negative sign. Got it? Yes, no? Okay. And then you can cancel out this m and m. So m gets cancelled out. Then L square, this L gets cancelled out. You can take that L on the other side. So you get alpha is, sorry, alpha is equal to minus of g upon L multiplied by theta. And what is alpha? Alpha is angular acceleration. So angular acceleration can be written as d2 theta by dt square. Okay, so d2 theta by dt square equals to minus of g upon L multiplied by theta. So see, this is equation of angular SHM. Okay, this is equation of angular SHM, and this is very similar to equation of linear SHM. d2x by dt square equals to minus of omega square x. Okay, minus of k upon m into x, right? So comparing these two equations, we get a hint that we have to replace this g upon L. We have to replace this g upon L by omega square, right? So we can write omega square. So we can write d2 theta by dt square is equal to minus of omega square theta. So we get differential equation of angular SHM where omega square is equal to g upon L, right? So therefore I'm sorry, omega is equal to square root of g upon L. And what is omega? Omega is 2 pi upon t. Okay, so it is 2 pi divided by t, the square root of g upon L, and therefore you get t equals to, okay, by shuffling the terms, you get 2 pi square root of L divided by g. So this is an equation for time period of simple pendulum. Okay, this is an expression for time period of simple pendulum. If you take reciprocal of that, or if you just write 2 pi f over here, then you get f equals to 1 upon 2 pi multiplied by square root of g upon L. This is the equation for frequency of simple pendulum. So is it clear? And actually we had seen this expression in dimensional analysis. Okay, so we had derived the time period of simple pendulum using dimensional analysis, but instead of this 2 pi, you get some constant k over there because you cannot find out the multiplicative factor using dimensions, right? All right, so this is simple pendulum. So now there is a special category of simple pendulum which is known as seconds pendulum, and it's there in your wall clock. Okay, so for that the time period is 2 seconds. How much is time period of seconds pendulum? It's 2 seconds. In 1 second it goes from left to right extreme. Okay, it hits there and makes some sound. Again it comes back, it hits the other end, makes some sound, right? So seconds pendulum, it has got time period of 2 seconds. So now you can put that over here, and putting that you get length of seconds pendulum. We get 2 equals to 2 pi multiplied by square root of L upon G. 2 and 2 gets cancelled, then we can square it. So we get 1 equals to pi square L upon G. Okay, so this is my G. Then from that you get length of seconds pendulum. L is equal to what? The G divided by pi square. So G is 9.8, pi square is near about same, okay, somewhat more than that. So seconds pendulum, length of seconds pendulum is 0.9 something, okay, in meters. Okay, so next digits we have to find out by doing calculation. So the point is the length of seconds pendulum is G divided by pi square. Okay, it depends heavily on the value of G, right? So we cannot have seconds pendulum of arbitrary length. Okay, so we cannot have a clock based upon pendulum in which length of the pendulum is arbitrary. Okay, so length of seconds pendulum is fixed. Got this? Yes, no?